So these are the three outputs we get for the modified Euler's method. And if you remember, a similar kind of values we had obtained while using the Euler's method as well as the improved Euler's method. You also know that we have the exact solution of this problem, and we can summarize all the results in the form of a table. I'm using the previous two method results from the previous lecture and these three results from this talk. So here we generate the ultimate table of values. The first column will be of x, and the second is for Euler's method, which we have done in the last lecture, and second is the improved Euler's method. Third is the today's method, which is the modified Euler's method, and the last one is the exact solution. So these are the heads under which we have to substitute the values. The values which we are looking for are 0.1, 0.2, and 0.3. And when we use the Euler's method, we got the result in the form of 0.1, 0.19, and 0.271. These were the results we obtained by using the Euler's method. And the improved Euler's method gave 0, 0.095, 0.095, and this is not 0, I'm sorry. So this is 0.095 at x.1 and 0.180975 and 0.258723, whatever it is. So these are the results we obtained in the previous lecture. The modified we have just obtained. These are the three results. The first result is 0.095, 0.180975, and 0.25878. So this is the 782. 258, 782, 7. This is 782. Okay, 782 is here. And the exact solution for this problem are 0.09516, 0.181269, 0.2591817, and you can increase the decimal places according to your requirement. Now you can see the ultimate comparison of all these three methods. So these two methods having the same answer almost, and whenever you make the comparison with the exact solution, so this indicates that the improved as well as the modified are more closer to the exact solution comparatively to the Euler's method. So this indicates that the improved and the modified are a little bit better comparatively to the Euler's method. So this was a simple problem on which we have applied these three methods. Now we take another example. Okay, the problem here is to solve, this is the differential equation, the form dy over dx equals to y minus 2x over y, along with the initial condition of y0 equals to 1, and within the domain of 0 to 0.2. This means the increment you have to make is 0.1. If I draw it here, you have to start from 0. This is of course x0, and then the first break will be at x1, this is 0.1, and then you have to be at the required place of number 2. The corresponding values are here, the initial values are given, this is 1 here, y1 you have to calculate, and y2 you have also to calculate. we are going to apply the Euler's method. And I believe you have some idea of the Euler's method in mind. So here you can make the comparison. Fxy is equals to y minus 2xy over y, along with this initial condition I'll be using. The formula for the Euler's method is ym plus 1 is equals to ym plus h times fxm ym. So this is the formula for the Euler's method. Now you can put the function's value here. We get ym plus h times f of xy will be replaced by this one. So this takes the form ym minus 2xm over ym. These are just the iterative recursive relations values we have to determine. Now on simplifying and putting the values of m starting from 0, we get y1, y0, h, y0 is here, 2x0 over y0. y0 and x0, we can use these two values. H is 0.1, which is given in the question. Putting all these into this format and simplifying, you will be getting the result. This is going to be equals to 1.1 after simplification. I hope you can verify of yourself. Similarly, for the next value for 1, y2 is equals to y1 plus h times y1 minus 2x1 over y1. x1 and y1, x1 is 0.2 and y1 we have just calculated. To put those values back into this part and simplifying, and h is also given. The ultimate result is 1.19181818 and so on. So this is the second output. So these are the two requirements, and we succeed in finding these two outputs. So you have to note down these two results. Then at the end we shall be summarizing the whole result in the form of a table. So there we will be putting these values back. Now we use the second method. The second method is the improved Euler's method. So the improved Euler's method the formula for the improved Euler's method, if you remember, we had drawn the formula for the improved Euler's method in the form of ym plus 1. This is equals to ym plus h by 2 times f of xm ym plus f of xm plus h ym plus h f of xm and ym. So this is the formula. This covers this part and the bracket is there. Okay. And now you have to put in the values. The function is this one. I can replace this quantity by y minus 2x over y. The inner part of the function, this one, can also be replaced by this. After doing this, then you have to replace the outer function. So the ultimate form, after replacing the functions into the format, you will be getting the recursive relation of the form ym plus h by 2 inside ym plus h into ym minus 2xm over ym minus 2 times xm plus h whole divided by ym plus h times ym minus 2xm over ym. So this will be the result you will be obtaining after putting this function in place of this part. Then here these will be replaced first, and then after doing this you have to replace this outer function, and on simplifying you will be getting this recursive relation. On the left side there is always ym plus 1. Now on using the value